Hi, my name is Patrick Geneva, and today I'm going to be talking about how to use a RealSense camera, how to perform calibration on that, and then use that as input into a state estimation algorithm, OpenVINS, to recover the 6-DoF pose. So this video is going to be in a bit of a unique format. I'm going to record it all in one take. It's going to be a little bit more casual. And so please be patient with if things go wrong. Feel free to skip forward to the different chapters. This video won't go into super detail on how to perform the best calibration or all the nuances of that. I recommend watching the other video on that. The main focus is basically to get the calibration and to start performing state estimation as quickly as possible from basically nothing. So first, let me talk about basically the sensor. So the sensor that I'm going to be using today is the T265. RealSense, I believe, doesn't make this anymore, but it's a nice stereo camera with a IMU. You could also use, for example, the D455, and a lot of these steps are going to be exactly the same. It's just that this is the one that I have on hand with a very long USB cord. So so first a little bit of self-promotion, and I'll guess kind of explaining the end goal. So our research group open sourced a project called OpenVINS. It's a state estimation system for researchers. It's a filter-based system with it tracks sparse visual features. I recommend checking it out, and I guess reading through the project and to fully grasp everything. But basically, actually already in the repository is a config that you can just directly use for the T265. But in this case, we're going to try to recreate this config from scratch. On the website, there's a guide for how to do calibration. I recommend following along with this guide. And this explains basically the process. First, we need to find the camera intrinsics and extrinsics between the left and the right stereo pair. And then we need to find the IMU noises and those different properties. And then finally, we need to perform calibration between the IMU and the camera, including the time offset. And in this case, we're going to be using, we're going to also try to calibrate the IMU intrinsics. So I guess first kind of explaining what my workspace looks like. So in my source folder, I have both caliber, Allen variance, ROS, and OpenVINS, and these have all been built. And so everything is good to go here. If you're building Caliber, I do recommend, so Caliber is the Visual-Inertial calibration toolbox that we recommend. It does multi-camera, Visual-Inertial, multi-IMU, and then also a rolling shutter. But if you do build this, I do recommend using the Docker image just because of its ease of use. But in this case, I built it from source, and I'm using ROS1. Caliber requires ROS1. So I guess the first thing we need to do is we need to get the data out of our sensor. And so to do that, we're going to use our, excuse me. To that, we're going to use our the RealSense driver. So you can install first libRealSense. I recommend installing this because it has the nice utilities. It has both the UDEVs, and it also has the tools to basically query the connected devices to help you debug. You can follow the Linux guide to basically install that. In this case, I have already done that. So basically, the process here, sudo apt install libRealsense to udev rules. That's the first one. And then the second one, which has different utilities, is the libRealsense 2 utilities. Finally, for your ROS distribution, we're going to install basically the ROS. So in this case, I'm using Noetic. no ROS, noetic, Realsense, sudo apt install rs noetic Realsense to camera. Okay, and so that will install it globally in my my ROS install. You could clone it and build it from source. In this case, it's just easier to install it and to install it globally here. So now that I have this, one of the command line utilities that should be installed is rs. So they have a whole bunch of Realsense utilities. In this case, the one I'm interested in is rs-enumerate-devices. And so you can see here it found the Realsense camera, the T265 that I have plugged in. And you can see that down here, importantly, you can see the different types of data that can be streamed. And so, for example, if you did have the D455, you would see different things here, and you could mix and match basically your streams that you want. Importantly, it is important to note that the accelerometer is actually 62 hertz, and so it's asynchronous, or it's a different frequency from the gyroscope. So actually, one of the important things that we'll need to do is we need to ensure that we unite, basically we combine the gyroscope and accelerometer together into one data stream. And that kind of, we'll talk more about that when we get there. So this is what we want. So now we want to create basically a launch to basically launch the corresponding ROS node and then publish those topics onto ROS. So actually the first thing we should do, we should get ROS core running. Okay, now we have ROS core. So now let's go ahead and talk about the ROS driver. And so this is what we installed globally, but this is basically where this is the source code. They now have, it's a ROS1 legacy branch. Basically here they have an example in their Realsense 2 camera launch, this Realsense T265. And so what I'm going to do here is I'm just going to copy this contents and I'm going to make a new file. And this is called realsense.launch. Okay, let's save that. Okay, I've copied all of their stuff in here. Save that. We don't need this warning. So now basically we have our, we can go in here and make our edits. So in this case, what we want to first do is we want to make sure we enable our two fish eyes. So true, true. The width and height were things that our rs-enumerate basically gave us. We have our width, we have our height. Okay, I'm going to call this T265. Typically, I like to name it the same as the device. So if I have multiple cameras plugged in, I know which one is which. Additionally, we can specify the serial number for this camera. Then we want to make sure that we enable our gyroscope. We don't need to enable the pose. And then finally down here, we have our unite method. Actually, let's specify so the gyroscope is 200, and this one is 62, I believe. Yes, okay. So the last important thing is this unite-IMU method. So if we just run this as is right now, and so now I'm in this this tutorial 2 folder here, and I just do ROS launch Realsense .launch. So it's going to launch. Given stream configuration is not fisheye stream index. Oh, I didn't specify the fisheye FPS. So that was 30 hertz, if I remember correctly. 30 hertz. Okay, there we go. So now if I launch it, hopefully we don't get that many warnings. Okay, everything is good. So now if I go back here and I do ROS topic list, you can see that we have all these topics. But importantly, so we have the image raw for the left, for the right. but we don't have, instead what we have is we have this, for the gyroscope we have some topics, and then for the accelerometer we have some topics. And so if we just copy this and we do ROS topic info on this, so this is a type sensors IMU, but it's just for the accelerometer. So if I do ROS topic echo this, you should see that basically only the accelerometer component of it is being filled in. And so this, you know, we need to have synchronized IMU and camera information. So we're going to use that. We're going to use this utility called unite-IMU method. If we go back to their page, they have this documented. They talk about this, and basically what we're going to do is we're going to use the linear interpolation one, where basically two sequential acceleration measurements are going to be interpolated in between, and that's going to combine the two. So put that there, and now we should be good to go. So now if we kill this and we now launch it, we should see here that we now have the T265 IMU, which has the full frequency, okay? For the full information, if we do ROS topic hertz, we can see that's getting published at 200 hertz as expected. ROS topic hertz, T265 fisheye 1 image raw here. You can see that our camera is being published at 30 hertz, and then finally we can do RQT image view, and we should get our camera feed here. And so this was the fisheye 1. So if I cover, in this case, the left, you can see that that's what I am covering. Okay, so we have now the live data, we have a view, and so now we can try to basically collect the our data. So to do that, we can record a ROS bag. So ROS bag record. What we're going to use is we're going to specify the topics here, and we're going to output to a specific name. Okay, and so ROS bag record output capital O. This one is going to be the static calibration. So this is just calibrating the camera intrinsics. And so then the topics that we're interested in are the image raw for 1, the image raw for 2. Notice that basically I'm recording the full camera frame rate, and then when I use caliber, I'm going to downsample that because I don't need the full camera rate. Okay, so now I have this. I'm just going to move this over so that I can see this, and then now I can actually get ready to do my calibration. And so I'm going to move it here in front of my board, making sure that I get all different angles, different skews, different distances, all these type of things. And so let me just, here you can see I'm going to hit enter. Okay, it's recording. So now make sure I get all the different views. Get all these. Get all these. Try to move to minimize motion blur. Get a couple bit further back, trying to fill out the whole the whole image plane. Okay, okay. Okay, and then I'm just gonna hit proceed. Okay, so we have recorded. And so now we have successfully recorded. Let's go ahead and take a look at our static bag. So we have over 49 seconds. We have 1,079 frames. Looks like we're good to go. Now we can try to actually perform calibration. Now, one of the key things that we do need is that we do need the, so we're going to do this multi-camera calibration. One of the things that we do need is we need the board, the target that we use. And so actually what I used is the Calibre default April grid 6x6. So I'm just going to download that config and put that in our folder here. Okay, and you can see this is what it contains. It contains the information about that board. And so this is important to make sure that our stereo correctly gets metric scale here. So now we can go through and we can run our camera calibration. We're going to specify 2 topics here, but now we need to talk about our camera model. And so this is a fisheye camera. So what we're going to do is we're going to use the pinhole projection model. We could use another one, but OpenVINS supports only pinhole models. But we do support basically the pinhole and the equidistant. Okay. So let's go ahead and try to create our command. So we're going to do ROS run calibrate cameras. Okay, just move this over a little bit. Now we're going to specify our target April 6x6 models pinhole equally. So I'm specifying 2 of them because I have a left and right stereo. Then my topics. So the first topic will be my cam 0. The second topic will be my cam 1. So in this case, we're going to specify the fisheye 1, then the fisheye 2. And then we're going to specify our bag static. And then we're going to specify the bag frequency, bag FREQ, and we're going to downsample to 10 hertz. So basically, instead of processing the full 30 hertz, we're going to process at 10 hertz. And this is okay because really what we need for the static calibration is basically unique views. So it doesn't make sense to try to process the 10. Okay, and then finally, to just double check, we're going to do show extraction, and this should show basically both our left and right camera extractions. Okay, so you can see it's correctly extracting the board. The reprojection errors look, I guess, relatively reasonable. They look like they're on and everything. Okay. And you can see that it downsampled or removed 1,000 images based on the frequency, and we're only processing 400 images in the full time. Okay. So it has filter outliers, and now we can see our result. So what we have here is our observation graph. If you had multiple cameras, then you would have more. You can see this is the number of mutual observations. There was 47,000. We can look at our camera system. Very nice. It looks like a stereo pair. We can look at our estimated poses. In this case, these are the poses that it selected as basically the subset of all 400. I think it selected 66 of the 400. And then finally, we can look at the reprojection. You can see here actually that, so one of the important things is you want to ensure that you have a Gaussian distribution. It actually looks like, yeah, it looks like the y-axis is more uncertain. So typically I would I would recalibrate this so that it'd be, a more perfect distribution. Additionally, this is, you can see there's quite a few out, or there's a long tail to the distribution. You want this to be as Gaussian as possible. So typically I would try to recalibrate this in the vertical direction, or not, I just collect another data set and try to get this to be as small as possible. But we'll take this as now. OpenVINS is able to perform online estimate or online calibration, so it should be able to correct for this. It's just that, this is something that your offline calibration should be better than this. This one, again, the X is plus or minus 1, but the Y is plus or minus, I say a little bit more than that. Relatively good coverage in terms of the whole FOV here. Maybe there wasn't enough at the very top. And then finally the outliers. Okay, so it's generated basically this report. If we look at basically our workspace tutorial 2, we now we can make a static folder. We can put all of our stuff into the static folder. And now the next step typically is to try to recover the IMU noises. And so Calibre has a whole wiki page talking about the IMU noise model, how to get this. Typically, you determine it experimentally using a Allen deviation or Allen variance chart. You record a very long data set of the IMU being static, and then from there you then process it. The tool that we recommend is this Allen variance ROS. This does take quite a bit of time, so we've kind of already done this. We've collected a 17-hour data set, and then I have already pre-processed it with this Allen variance. And so what we can do, where's this? What we can do is we can basically just make a new folder called static IMU, and then in here I'm going to make a new thing called imu.yaml. This is typically what would be generated, and what we found from our 17-hour data set was the following for the T265. The white noise we have multiplied times 5, so typically you inflate to basically take into account other unmodeled errors, and so the white noises we multiplied by 5 from the Allen variance chart, and then the random walks we multiplied by 10. Okay, and this is our ROS topic and the message frequency. So now we can go ahead and we can try to perform visual inertial calibration. And so to do that, Calibre again has a wiki on how to do this. We've already recovered our noises, but we want to collect the images. And so the important thing is we need to make sure we excite all IMU axes. Typically I try to do compound angles. We want to keep the motion blur low. To do that, you want to have a high frame rate and then good light. And so additionally, you want to make sure that your IMU has good timestamps with low jitter, and we can inspect that after we perform calibration. So let's go ahead and let's try to perform or collect a data set. Again, let me pull up basically the ROS bag here. The important thing is that we also need to do the T265/IMU, and we're going to call this bag dynamic. Okay. There we go. Now we have a bag, and then sensor. Get myself all set up here. So now enter. So everything is recording okay. To basically keeping the target in the frame. Excite all IMU axes. Rotate enough so we get a nice moment arm for the gyroscope frame. Finally, we can just go here and do Control-C. Okay. So now we're here. We can take a look, raw bag info, dynamic. Take a look. We have our IMU, it's 58 seconds long. We have our images. And now we can try to perform our visual inertial calibration. So we're going to do ROS run, calibrate, IMU camera, the IMU model we're going to use is, so there's many different types of IMU models. The specific one we're going to be using is the scale misaligned, which basically you can read. I recommend reading the Extending Caliber paper, which basically outlines all these different camera or these IMU values. There's like there's skew, there's scale, there's the rotation between the gyroscope and accelerometer. These are all things that that can help improve performance. And so for the T265, I know that basically the gyroscope has a pretty large both scale and skew correction, if I remember correctly. So we're going to go ahead and try to use the scale misaligned model. So let me get back to the command. So the IMU models, in this case, we only have a single IMU, so we're going to use scale misaligned. Hopefully that's spelled correctly. The reprojection sigma for our camera was 1 pixel. Maybe I could increase this because our camera calibration is pretty bad here. Let's just run this and see what it does. Our target here is the April. The IMU is going to be in the IMU static. These are the IMU noises. That's that YAML that we just created. Make sure that I saved it. I did save it. Then our cams. This is going to be our cam chain, which was in static. Static cam chain. Okay. Then our bag here is going to be called dynamic, and then show extraction. We're just going to inspect our extraction again. Let's see if we scale misaligned model is incorrect. Okay, let's just run the command and see what the model is actually called. Oh, scale misalignment. Okay, very well. Okay, there we go. So let's see how this goes. It's going to read in the IMU. Let's see what the extractions are going to look like. You can see here also it reports the reprojection error. And you could run into troubles if, for example, the board, you lose tracking of it partway through because you're really relying on the board to provide a pose to constrain basically the inertial information. So Calibre uses a continuous time representation. So basically you use these poses, then you take derivatives of them, and you can directly write the acceleration and angular velocity as a function of those B-spline derivatives. Yeah, so right there, this is, maybe I shouldn't be as extreme as this. You can see there's a little bit of motion blur here. But overall, the tracking seems to be reasonable. And you can also, cut the bag so that it it's a smaller portion of the whole thing. You don't need that super long data sets. In this case, I recorded a 50-second data set. Typically, you need, maybe 30 seconds worth of data if you have enough motion in that 30 seconds. You're just more likely to include all the correct motions if you record a longer data set. Definitely nothing above a minute, for sure. Okay, let's just assume that all goes okay. I'm just going to Control-C it, and then disable the show distractions, and then we'll let this all time in here, and we'll just let this go, and we'll pick up after this finishes. Okay, so it has finished. Let's take a look at the report. So you can see it found these camera to IMU. So this is IMU to cam 0, IMU to cam 1 transformations. The time offset is about 3.6 milliseconds. Then you have the scale misaligned IMU model with all these different matrices here. And then looking at the actual report here, let's take a look. So this is the trajectory that it recovered. Looking at the IMU sampling rate, this is basically as close to good as you would want. Basically, you could see that every sequential IMU reading had a 5 millisecond time difference. If you see something that you have different groupings, you could have a buffering problem or a driver problem. In this case, we don't have to worry about that. We can look at the IMU errors. So right here, it looks like things are going outside the 3 sigma bound, which is not good. The bias mostly stays within the 3 sigma bound. The angular velocities, mostly besides these spikes, and this x-axis is going out of bounds. The gyroscope bias definitely goes out of bounds. Probably this is due to the poor image. So typically you'd want to make sure that all those are in bounds to have a good calibration. So here we can see again that we have this oblong shape, and also, at least here everything's within the dotted circle, so the 3 sigma bound. And then here we have a similar thing. It's not a a nice normal distribution in 2D, but at least everything is inside the 3 sigma bound. So it's going to save all that stuff to file. We can go ahead and make a dynamic folder. So typically I would re-record both the dynamic and the static for this example, but we're going to forge forward just for the sake of it. And so one of the things that we want to look at is we can look at the dynamic results here. So the first thing actually we forgot to discuss about the camera calibration is the baseline. And so this basically says that we have an identity transformation between the two cameras and a baseline of about 6.4 centimeters, which for that camera it looks reasonable. I mean, it looks like 5. Maybe it's a little bit more. I have to get a ruler, but this is reasonable. You can see here that basically you have the IMU is to the cam 0 is basically to the right of the IMU, and then the cam 1 is to the left of the IMU. And so, or it could be vice versa. I'm not quite sure about which axis the X is. But this looks reasonable. It is interesting that we have negatives here. I mean, it looks like identity, but then you have this negative here. We'll have to see if this works, basically. Finally, we also have the IMU intrinsic parameters. So now that we have this, let's go ahead and try to make a OpenVINS configuration. So basically the thought process here, I have OpenVINS already installed. There's a guide on the documentation website on how to install OpenVINS for both ROS 1 and 2. In this case, we're using the ROS 1 version, but Calibre uses ROS 1, so you have to at least use Calibre in ROS 1 in it, or you could use a Docker container, but it's still ROS 1. And so we're going to be using the development 2.7 branch. Probably by the time you see this video, this has been merged into the master. This is the one that has the IMU intrinsic support. And so what we're going to do is basically we are going to copy one of the example configurations. And so in this case, we go in here, src, OpenVINS, config, and we're just going to actually copy the T265 one. We're going to go back up here, I'm going to paste this, and we're going to rename this rs custom. Okay, and so now we can look at what these config files are. So the reason I use this is that this actually already has masks. So if you have a fisheye camera, it makes sense you only want to extract the center region, and so we're just going to take advantage that we have those masks. The estimator config, we really don't have to do anything here. This is just the default values. Typically what you need to tune is, for example, the initialization thresholds. So basically this is the initialize once you pick it up. Sometimes with different IMU, you need to change these values, but we'll just leave them as the default for now. And then the cam chain. So in this case, we can copy our dynamic one. So we're going to go, the important thing is at the top of these files have to have the %YAML. So we can go to our cam chain. We can copy this. And we can see here that we can actually compare the the original one to this one, so you can take a look. So the original one, ooh, they look very different actually. Interesting. Okay, yeah, we'll have to see if this one even works. So this is the original T265 one that I have. You can see that at least the intrinsics are, I guess that's 10 centimeter. The camera centers look about the same. Distortion, it's about the same. Maybe these distortions are a bit bigger, but this you see this translation is very different from the one that we found. So we'll have to see if this config works. So that's that. Then we have our IMU chain. So the same thing here. We can go to our IMU static here, and we can copy these values. We can put them here. Okay. For now, let's just assume we don't have the IMU intrinsics. Maybe we might have to add them. So now, what we're going to do is we're going to run the built-in OpenVINS subscribe.launch file. And so I guess the first thing we should do is we can, so we don't need this. We do rvis -d src OpenVINS ov msckf launch display.rvis. So this should be the rvis display here. Now we can take a look at this subscribe.launch. And so what we're going to do is we're going to specify our config file is basically the one that we've created. And so this will be basically, it's going to read all the data in from this config file. So what we can do is we do ros launch open, it's first source, ros launch open oh, it's not OVMCKF, subscribe. And then the parameter is config path :equal, and then we are going to specify our rs custom. Where was it? It was rs custom slash. This might have to be an absolute path. I'm not quite sure. Yeah, okay, it does. So then we'll do slash home slash or pwd. There we go. That's an absolute path. And let's see what skip spaces, incorrect indentation. Okay. Let's take a look. That's a very common thing. Yes, so these need to be indented as compared to the how did I close that? That's compared to the caliber one. So let's take a look at this. So hopefully the thing does not fly away. Looks like things are okay, maybe. I don't know if that's just because we calibrate or we have online calibration running, but I guess you can't really see this. Let me see, how do I I guess that will maybe I should make the TF bigger for you guys. Something like this. So now I'm in the middle of the room, back here, 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 here. Okay, so it seems like things are okay. So this is the board there. You can see that. I guess one thing we can do is we can keep MSCKF features and try to see what a map of the room looks like. To see what it looks like. Probably some more pixels. Let's see, do we see? So I mean this. Yeah, this looks like the board, correct? That's the board right there. There you go. Okay. Well, things I guess are doing okay. Let's see if we can get the and you see it flies away because we don't have zero velocity update running. Let's see if we can get the IMU intrinsics to work. So here, basically we want to take our IMU, not this one, but our dynamic IMU, and let's do 2 columns. So we can see that we have for the, so we're using the caliber model, the TA, let me see, I gotta remember what all these different things are. So yes, so this is IMU to gyro. So that should be this one. And then TW should be no, TA, this one. And then the IMU to accelerometer, that's identity for the caliber model. Then we have the M for the gyroscope, which would be TG. And then finally, the this one should be the gravity sensitivity, which is in this case, oh, oops, wait, this should be TW. So this is TW. So what we should see is that, so this looks like an identity transformation here. The TW here does have, it looks like, well, this one's actually isn't that bad. Oh, is it the TA that's bad? Yeah. So you see this off diagonal here is very, very large. So that means there's a large amount of skew here. And also, as compared to, you see the gyroscope has ones on the diagonal. Let me make sure I copy this correctly. Yes. So the this has ones, so that means that the scale is not that incorrect on the gyroscope. But the accelerometer, on the other hand, you can see here it's like a 0.02 correction or 0.01 correction, which is relatively large. But the this off diagonal seems to be pretty big. And then the gravity sensitivity, you can see that, I mean, this one's non-zero, but in general, these are all, the closer to zero basically means that the accelerometer doesn't affect the gyroscope. So, okay, let's save that and let's see if that makes any difference. Let's see if it flies away, because right now we're not going to calibrate it. So let's just see if this this flies away or not. Oh, okay. There we go. So hopefully I'm not quite sure. I would have to evaluate this quantitatively with either our OptiTrack system or something else. But now we're applying our IMU intrinsics. We can go ahead, and because I have handheld motion, I can go ahead and enable calibration for the IMU intrinsics, actually. Where's my RS custom estimator? So typically we don't recommend calibrating these because you don't have a dynamic enough motion and they're very degenerate. But in this case, because I'm doing handheld, things hopefully should be okay. And let's, so you can see down here, I am now calibrating. It looks like we'll have to see what their final values are and see if they are close to caliber. If so, then our caliber calibration already was pretty rough with a very poor reprojection there. So we'll see if let's go here, Control C it, and we can now compare against what caliber gave us. This is typically good practice. Let's see. So the first thing is IMU acceleration. That's identity because we don't calibrate that in the caliber model. The IMU to gyro rotation is here. Yeah, it's all constants. It looked here that mainly the TG now became very, very close to 0. So maybe this one here is incorrect. TW, yes, TW, that's what we had as identity with very, it's not that much here with the skew symmetric, but this one seemed to stay basically. So it looks like we have an agreement basically between this and the other one. You can also check the the camera transformation, the camera intrinsics, and then of course the time offset. I hope that this guide helped, and I hope that by the end of this you are comfortable basically running OpenVINS or performing calibration and then running OpenVINS yourself. And I guess another thing you can also do, max cameras is 1. So in this case, we're going to run monocular, which should be very, very fast. Yeah, 80, 70 hertz. But yeah, so I hope that this guide helped you and that you have learned the process of calibration, and then how to also a basic introduction of OpenVINS. Okay. Thank you very much, and feel free to check out my other tutorials, specifically a bit more about how to the more in-depth